Okay, hopefully this kind of works. So I'm explaining problem 2.9 from problem set number 3. And basically, you have an electrostatic field, and it's given by E equals lambda times I hat x plus j hat y. I thought I'd kind of draw out a visual of that over here, which shows that in the xy plane, this electric field is going out radially from the origin, and you can extend that all the way up the z-axis, and it gets stronger as it's further away from the origin. Just thought it was helpful to look at that. So we have to use Gauss's law to find the total charge enclosed by a surface. This is the surface right here. It is a half cylinder with its flat part sitting on the xy plane at z equals 0, with a length h and a radius r of the cylinder. So to start out, we want to find the surfaces. So surface 1 is described by this equation that they gave us, z equals r squared minus y squared to the 1/2. S2, second surface, is this half circle over here, and S3 is this half circle on this side. And those are just described by the x value where they sit. So this first one sits at x equals h over 2, and the other one at negative h over 2. And the final surface is this surface number 4, and that is at z equals 0. So now we want to find the normal vector for each of these. So that's the little n hat. So n hat 1. There's two ways to find this. You can use the equation 2.4, which brings you through in like a specific equation to get the answer, or you can use intuition. Both worked for me in this case, but we'll go through the equation way because it's very explicit. So this is the equation 2.4 right here, and we want to find our function in terms of x and y. So that function for us is the function that they give us for z. That's going back over here. Our function in terms of x and y is this z function. So you notice there is no x in it. So that's why when we find the derivative of that with respects to x, we get 0. And then the derivative with respects to y, you can solve that out and you get negative y over the square root of r squared minus y squared. So plugging those values back into this equation, we plug them in there, and then through some simplification, you get that their n hat for the first surface is y j hat plus k hat z over the square root of z squared plus y squared. So now we'll bring in Gauss's law here now that we have an equation for our field, which is this guy right here, the equation for our field, and we have our n hat right up here. We can plug those in and work through this Gauss's law. But this is where, for this surface, since it's a curved surface in all three planes, we want to go back to that equation 213 in the textbook, and we solve that out. So the final answer, or the what we get when we do this, saying? When we take this dot product here, the final dot product is this guy, but you use equation 2.13 to get to that. So this is equation 2.13 from the textbook, and you go through with all of like breaking it into components, and basically fx is x lambda, fy is y lambda, and fz is 0 because there's no z component. These come from this equation here where you're taking the I and j and k components of this equation. There is no k component. That's why this is 0. And then you can also find the derivative of the initial function that we found, of the functions that we found earlier. So the same thing is up here to plug into this equation, and then you get this right there. So now that we have that looking nice and pretty, you want to set your bounds. So the bounds can go back to that picture where x went from negative h over 2 to h over 2, and y went from negative r to positive r. Fairly straightforward if you look at the picture. And then on this side, you can do the integral with respects to x first because there's no x in here. So that just comes out as simply h when you subtract negative h over 2 from h over 2. So then we get this, and then this integral was given to us but with the rest of the homework. So that integral gives you this form here, which is kind of hard to see in this glare. So lambda h equals negative 1/2 y root r squared minus y squared plus 1/2 r squared, inverse tangent of y over root r squared minus y squared from negative r to r. So one trick here is you might wonder, hey, look, this goes to 0 and you get something illegal there. But when inverse tangent goes to 0, that actually means that it is going to pi over 2. So that inverse tangent thing, when that has 0 on the bottom, which it does every time, is just pi over 2. So when we evaluate that, we get 1/2 of this over that, and you get h r squared pi lambda over 2, which is the flux through your first surface. So that's the flux through the first surface. Now we have 3 more surfaces to do. These ones are a little bit easier. I didn't actually write this one out, but I'm going to talk about it now. The fourth surface, S4, is that rectangle on the bottom, and it lies in the XY plane. And since it is completely parallel to our electric field, it has no flux, so that one is 0. So, yeah. Then, so we want to find n hat for the second and third surface, and that's just I and negative I, because their surfaces, they lie in the YZ plane, so their normal vector will be in the X plane, which is just I hat. So then we can do these integrals where you do the dot product between them using Gauss's law. And when you do that dot product, it just leaves you with x because you're just dotting the i's, which gives you x. Dot the i's, give you x. X in this case is a constant, X equals h over 2 or negative h over 2. So you can pull that out and you get lambda h over 2 times surface area. So these are just the surface area of these integrals now. So you can factor out this lambda h over 2 and have two half circles, which is just the whole circle, which is pi r squared. So you get pi r squared times lambda h over 2, which gives you this right here. That's the flux through those two. So now we have 1, 2, 3, and the fourth is 0, as I said, because it lies completely in the same plane as where the electric field is, so it doesn't have any contribution. So all we have to do is add them all up. So we have from the first plane, or first surface, and then from surfaces 2 and 3, and surface 4 is 0. So that equals that, and then you do this, and you get that as your answer. All right, that should be good.